All right, today's lesson is section 7-8, and I'm going to introduce you to another of what we call the parent functions. And we're going to learn today how to graph this parent function y equals the square root of x. And then we're going to talk about, like we've done in the past, do a little review of translations. How do we translate? Or another word for translate is to move or shift. We've looked at translating other parent functions in first semester, and we're actually going to review those today, and then we're going to talk about how to translate this parent. What does this parent look like, and then how do we translate it? That'll be the focus of section 7-8. So before we get into today, I thought it might be good to just step back and go back into first semester material. And let's talk about the family, or we could say the group of functions that we call the parent functions, because you're going to need to know what these parent functions are as you head into pre-calculus and calculus. You need to make these very familiar to yourself. And tomorrow on your 6 and 60, I'm going to show you the graphs of parent functions, and you're going to write down the equation that is represented. So pay close attention, review. You've seen these before, but make sure you remember headed into tomorrow. Okay, so I'm going to get a volunteer. Just raise your hand. Give me a description. Just describe for me what that parent function y equals x looks like. Dusty.
It's just a straight line.
Okay, and what else do we know about it? Straight line passing through... Okay, passing through the origin. What slope does it have?
That is a slope of 1.
Positive 1. Okay, that's a good description. Here is the actual line, the parent function that we call y equals x. Okay, so you should know that. It's important. We've looked at some of the things that y equals x does for us. We're going to talk about that now. But you should be able to identify this line as a parent function y equals x. Now I don't have the version y equals the opposite of x, but that's easy enough to determine. What does that negative sign in front of x do to this graph? Kiana?
It just makes it angle the opposite direction.
Okay, so now it's a -1 slope, and it still goes to the origin, but it passes through in this direction. Okay, so that's the effect of the minus sign on this parent. It's actually two different parents. The positive and the negative would go the other direction. Very good. Okay. Somebody else tell me what this parent function looks like. This y equals the absolute value of x. Anybody want to take that one, Ben?
It's a V from the origin.
Very good. It's a V shape. Remember the word value. If you think of the V in value, that always tells you what these should look like. And he also said something good. It has a vertex at the origin. So let me give you the picture. This is the actual graph of the parent function y equals the absolute value of x. Okay? And once again, I don't have it on a separate graph, but just somebody tell me what happens to the graph when I include the minus sign in front of the absolute value. Justin? Okay, so we use the word, and you'll hear this again from time to time, we use the word reflect. He's exactly right. It does open downward. But anytime you have minus in front like this, the effect of that is to just pick this red V up and flip it over the x-axis. You always flip over the x-axis, or we use the word reflects over the x-axis. Very good. All right, somebody else give me a general description of this parent function, y equals x squared. Let me get somebody that hasn't answered yet. Anybody want to volunteer? Benji.
Isn't that a U?
It is. He said U, or you could have said parabola. Okay. And how does it open? Upward. And now it opens down, or it flips over the x-axis if you include the minus in front. All right, so very good. You guys are doing real well with this. There's the actual graph of y equals x squared. It's just a U vertex at the origin. Well then, after we got sort of familiar with the parent functions, we introduced this word translation. And another word for translation is shift or move or transfer. Like, for example, what is the effect of including my blue part in with this parent function? What is the effect of this? What does that do to the parent? It causes it to shift from its original location, but where? Yeah.
Is it 3 units to the right?
Very good. She nailed it. It's moving because it's inside the parentheses. That always, if it's inside the parentheses, it means horizontal movement. And she said 3 to the right. That's our H number. And so here's the result of including that -3. It takes the red U shape and it shifts all the points on it 3 places to the right. Good job. All right, give me somebody else volunteer if I include this as part of the translation. Now what are we doing to the blue parabola? I think I'm going to get Lily. Up 4. Good job. And if it were minus, it'd be down 4. So there's the result. We started with the red here, the parent. We went 3 to the right, the horizontal shift. And then we included a 4 shift up. And that's where we land. That's our stopping point. So here's the reason why I wanted to review with you these principles of translation. And it's because, first of all, we're going to learn a new parent function to add to our list. We just looked at several parents. Well, now we're going to add another one. Okay, so to go along with y equals x, y equals absolute value of x, y equals x squared, and then the opposites of all of those, now we're going to add to that list y equals the square root of x. Before we just jump right in and graph, I want to build a table, and then eventually we're going to answer this question. What is the domain? Well, yesterday we talked about, or the day before, we talked about domain, and we said one good word that could be used as a synonym for domain would be input. So what I'm talking about here is, what are numbers that are okay, permissible, to be used as inputs? And conversely, there are some numbers that are not okay to be used as inputs. So first of all, let's just make a little table, and somebody raise your hand and give me a good input for x into this function. Chase.
4.
I like that. Chase, why'd you choose 4?
Because I do not know exactly.
Oh, that's a good answer. Yeah.
It's a perfect square.
Yeah, isn't the square root of 4 just a regular number 2? Well, would Chase, sorry, would Chase have been okay to choose 5 as an input?
No, it wouldn't.
I mean, would it be illegal?
No.
No.
It'd just be harder.
It would be harder because what's the square root of 5? Well, it's a decimal. It's 2.2 something, and we'd have to guesstimate on the graph where that would be. So if we can stick with just regular numbers to plot, that makes graphing a lot easier. Somebody else give me another good input. Somebody else. Abby. 1. I like that. What's the square root of 1? Okay. Very good. Blake.
16.
Okay. I don't want to go quite that high. That's okay. But our graph paper a lot of times doesn't go that high. So what about another one, Blake? 9. Okay. And what would the output be?
3.
Good. One more, smaller.
0.
0. What's the square root of 0?
0.
Very good. So what I want you to do is on your graph paper, I want you to find an empty graph section, and I want you to plot these 4 points. The origin, 1, 1, 4, 2, 9, 3. Okay, so let's talk for just a second. Now let's talk about, we've listed some numbers that are good inputs. What are some numbers that are not allowed? They're illegal inputs. Yes?
Negative 247.
Okay, well I will, he said negative 247, he's right, but I'll just say it this way. Negative anything. What's the square root of a negative number? It's not real. And we're interested in plotting only real numbers. So I'm going to back up a slide, and I'm going to state officially what our domain is using an inequality. My domain is going to be all real numbers, but I'm going to limit that just, well, a lot. Here's a symbol that you'll see later on in math, such that, that bar, literally in words, it reads such that. So here's a description of the real numbers that we can use. Only those numbers that fit this description can be used as inputs. Just the numbers 0 and higher. For that reason, the graph of this parent function looks like this. It's sort of like a curved ray. It's only one directional. Since we cannot use negative numbers as inputs, this is like it's like a starting point. This graph does not, so please, I have people that make this mistake on the test. They try to draw this graph like this. Well, that's not true. What you've shown me here is it's okay to put negative numbers in as inputs. Well, it's not okay, because if we do, we get unreal numbers. So this graph has a starting point at the origin, if it's the parent, and then it moves continually positive. And it continually gets a little higher as we go. But basically, we use these 4 points as a reference when we're talking about the parent of this. You're always good. These points are always true to be used for this parent function, y equals the square root of x. Okay? Any questions so far? All right, so now that we've looked at the parent, let's look at translations of the parent. Well, just keep in mind those translation principles are still true, just like they were with parabolas and absolute value. So for example, I'm showing +3 outside of the radical. Okay, well let me go back as a review just to connect. When this was a parabola and I had a number being added that was not in parentheses, we said this represented vertical movement of the parent. Well, the same is true here. When the number is being added or subtracted outside of the radical, that represents a vertical shift. And since it's positive, or +3, then we're going to be moving up 3 places. So, what I'm going to do here is optional. I'm going to leave this up to you. Some people like to do this. If you don't want to do this, it's okay. What I'm going to do, I'm not going to draw the whole curve, but I'm just going to plot those 4 points that we use to basically identify the parent function. And some people like to do that as a reference. This is where I start, and then this is how much I move from those points. Okay. Some people also like to use colors, like the parent in one color and then the graph, the answer graph, in a different color. So this is one of those times where it's okay to use pen. We typically don't. But if that helps you, that's perfectly okay. All right, so what we're going to do is we're going to take this parent function, which is represented by my 4 blue dots, and we're going to shift all 4 of them 3 places up. And that will give us our answer. Just take each of the 4, and from their spot, just count 3 units upward, and we're going to connect those dots, and that will be the graph. So this is the parent, y equals the square root of x, shifted 3 places up. Okay, does anybody have a question about that? So if this were one of your homework problems, that would be it. Some of these will probably not take you very long to do. Okay, well now let's look at the other shift. Notice now I've got -2, but it's under the radical. So that would be the same thing as what we were doing when it was a parabola, for example, as the number being inside the parentheses. Remember that? Inside the parentheses, that meant shift the parabola 2 places to the right. Well, same idea here. We're just going to take that parent function. So once again, here are the 4 dots for the parent. And I'm going to take each of those 4 dots, and according to this, I'm going to move each of them 2 places to the right. Under the radical is horizontal. Outside of the radical is vertical. Okay, and so the red represents the graph of this translation. All right, any questions about that? Everybody good? Okay. Well, you don't have to write this down, but let's just again make a connection to previously learned stuff. Somebody tell me there's really 3 things that are happening to this original parent, y = x squared. Just go left to right and tell me all 3 things. Give me your impression of what's happening to the parent here. I think Benji was first.
The negative makes it turn upside down.
Okay, flips it over the x-axis.
The -5 makes it go 5 to the right.
Okay, I would say it's just the 5, but okay.
And then the 6 makes it go up 6.
Very good. Okay, but the key point that I wanted to take away from this is this minus sign, that it flips or reflects the graph over the x-axis. So now let's look at the opposite of the square root of x. Here's the positive, and we've looked at that several times. So when you put the minus sign, it basically picks it up and it flips that original parent over the x-axis so that it looks like this. It's almost like the x-axis is a mirror. I missed that one. But the same translation rules apply. You know, you don't have to graph this, but if, for example, I did this, well, now we're taking this upside down, this red graph, and we're shifting it 5 places to the left, all the points. Okay, but it starts with this graph that falls underneath the x-axis because of the negative. All right, is that clear? Any questions? Everybody good? Okay, I just have one more slide, and that's going to conclude this lesson. I want to introduce you to what is vertical stretch and what is vertical compression. Well, you can probably conclude that stretch means that we're going to make bigger. Compression implies that we're going to shrink. So I've given you an example of each. The red is an example of vertical stretch, and the reason why we call it that is multiplying by 3, which is not a fraction or a decimal, basically has the effect of tripling the size of the parent. So it's going to make it bigger further away from the x-axis. And multiplying by a decimal or a fraction, like 0.5, makes the original parent actually shrink or become closer to the x-axis. So I just want to show you an example of each, and then that'll wrap this up. So let's put the parent back up here. Here's y = the square root of x, just the points. Just to give us something to look at. Okay, the effect of this multiplying by any number, in this case it's 3, if you think about this, it makes sense. If I'm stretching this, I'm stretching this way. I'm stretching vertically. I'm taking this parent and I'm either making it become bigger this way, or if it were a negative number, I'd be making it bigger this way. But in any case, I am stretching vertically. And which axis runs vertically? Yeah,
Y.
the y. All right, so if you'll keep that in mind, when we multiply by 3, we're actually only multiplying the y coordinates of each of these points by 3, just the y, because vertical implies moving just like the y-axis moves. All right, so let's just take, for example, what's the y coordinate of the origin? 0. And what's 0 times 3? 0. So the effect on this point of multiplying by 3 is no effect. Okay? Well, let's move to the next point. Here's 1, 1. Y coordinate 1. Well, what's 1 times 3? Okay, so the effect of multiplying by 3 on this point is to relocate it basically from its current spot to 1, 3. Notice how I just multiplied the y coordinate only by 3. Okay, let's move over to this point. That's 4, 2. So if I multiply the y coordinate 2 by 3, I get the point 4, 6, right? 2 times 3 is 6. So instead of being here on the parent, I'm going to go up to here to represent the stretch, 4, 6. Here's the point 9, 3, y coordinate 3. Well, if I multiply 3 times 3, I get 9. So the effect is, instead of being here on the parent, I'm going to go up to 9, 9. And the red dots represent multiplying the parent by 3. And that's an example of vertical stretch. Okay, real quick look at compression. Now we're going to multiply by a half, just the y's. Okay, what's the effect of that on the origin point? 0. 0 times anything is 0. What about this point? 1, 1. It's going to be 1, what? 1 half. Yeah, we're just multiplying the y coordinate by 1 half in this case. This is 4, 2 on the parent, but when you multiply 2 times a half, what do you get? You get 1. And when you multiply 3 times a half, you get 1 1/2. So those green dots represent a compressed parent, which is the effect of multiplying, in this case, by a half. So I just wanted to give you an example of what stretch looks like and then what compression looks like, making it shrink or become closer to the x-axis. Any questions? That's all for your notes. You're doing evens on this page, and don't forget we're going to check what you have not done from section 7 also in addition to this. And just email me or come to academic support in the morning, or you can see me after school today if you have any questions. I'll be here.